All right. Good morning, guys. Again, we're going to discuss derivative and different discussion. The student should be able to find the derivatives of algebraic functions using chain rule. Okay, so let's discuss what chain rule is all about. Now, here in the given examples, we have four functions from the left and four from the right. So if we're going to observe the functions given on the left are simpler compare to the functions on the right. Okay, and here you can, as it says here, now without the chain rule, which means we can perform this, we can differentiate these four functions from the right, or sorry, from the left without using chain rule. Technically, we're using chain rule, and every time we differentiate functions, but sometimes we omit some steps there since the variables being used are quite simple, or the functions given are quite simple. Okay, so later I'm going to explain why. And on the functions from the right are quite more complex than the functions on the left. So if we're going to look at it, now x squared plus 4, x squared plus 4 is a radicand, all right? Or it is an expression inside the radical symbol, which is the square root symbol, okay? So which means that we can associate this function as or we can treat this function as a composite function. So how do we do that? So here, let me just use my pen. So I could say that g of x is equal to x squared plus 4. So I could say that f of x is equal to a square root of x. Okay, so we could say, or we could write it in a form of composite expression or composite function expression. So this becomes f of g of x is equal to the square root of x squared plus 4. Okay, this is only for example number 1. Now, composite functions can be differentiated plus with the use of chain rule. Okay, and other functions as well. Now, we will be dealing with this chain rule method later once we deal with more examples. Also, we can use, in example number 2, we can use x squared plus 1 as the g, and the f of x is the outer function. And this is also the inner function, the g, and the outer function is x raised to 5, and the inner function g, and f of x is equal to the cube root of x, something like that. Okay, so let's try defining what the chain rule is. So here, the chain rule says that if g is differentiable at x and f is differentiable at g of x, then the composite function f, capital F, is equal to f circle g, defined by the function of f of x is equal to f, small letter f, of g of x, and is differentiable at x, and f prime is given by the product of the derivative of f, okay, of g of x times the derivative of g of x. So this is now the definition of the and also the rule of using or applying the chain rule in a given composite function. So in Leibniz notation, we can rewrite this in this form. So if y is equal to f of u and u is equal to g of x are both differentiable functions, then we can use this formula or equation to solve for the derivatives of the given function y. Okay. Now, for me as a teacher, I prefer this one, but you can also use this. Okay, it depends on how you perceive the solutions, or the what's this the process of differentiating a function given a composite function. Okay, now either you can use either, and you'll get the same answer, of course. So how do we identify the functions in a composite function? Now here, now for example, we have f of g of x. we usually say or call the function which is inside of f as the inner function, okay? And the f here, which is the outer, of course. And the g of x here can be denoted as u, as let's be used on how to differentiate functions with the use of chain rule. All right, you can use this as well. And again, you can use any type of expressions or way of writing down the composite functions. Okay, so let's try solving this, solving problems. Okay, so let's have example number 2. Find the derivatives of f of x is equal to the square root of x squared plus 4. Now here, we can do two methods. We can use the usual way, and the other one is with the use of u. All right, so let's start solving. Let me just change the color to white. We have method 1. Okay, now f of x, I am just copying the problem. So x squared, plus 4. Okay, square root of x squared plus 4. Now here, guys, what do here is for me to easily see the the exponent, okay, here to as exponential rather than using radicand. However, you can solve this directly with the use of the radical symbol or the radical expression. All right, so this is x squared plus 4 raised to 1/2. And if we're going to, let's say this is y, so as we could easily write it down, okay? So y prime is equal to, now the usual way, again, let's just have a short review on how we differentiate powers, all right, or functions, simple functions. So let's say y is equal to x raised to n. And of course, this must be differentiable. And this is a polynomial where n is a real number, okay? Or sorry, or n is a rational number, all right? So y prime is equal to n x raised to n minus 1. So the exponent will be written down as a coefficient, and the given expression, okay, is being copied, but the exponent should be deducted by 1. Right? So this is now the rule. And of course, the x here should be differentiated still using chain rule. However, since x is the derivative of x is just equal to 1, we don't do that anymore. But for the sake of chain rule context, all right, we do this. So this becomes nx raised to n minus 1, okay? Because this is just equal to 1 or 1. So nx raised to n minus 1. So it's same as not dealing with this anymore since this is just equal to 1. However, again, for the sake of chain rule, we usually do this, all right, for you not to be mistaken once you try to differentiate functions which are composite. Okay, but again, if it's just simple function, no need for you to do this. So let's start doing this. So we have, again, we just copy the exponent and put it or write it as a coefficient. And then we copy the base plus 4 raised to 1/2 minus 1, of course. And since we have another function here, okay, this one, all right, so it's just like the x here, the base. So we need to differentiate x squared plus 4. So x squared plus 4, and we need to differentiate that. This is a prime, okay? A prime, and which means we still need to differentiate this expression. So let's copy. There we go. And x squared plus 4 raised to negative 1/2. And what's the derivative of x squared plus 4? That's 2x. Okay, and I can cancel out 2. So we can now simplify this expression. I can cancel this out. I can cancel this out. There we go. And our final answer is x over, of course, this is negative, so this becomes x squared, the square root of x squared plus 4. All right, so this is now our final answer for this problem. Okay, So that's method one. And let's use method two and let's see if we'll get the same answer as this. So with the use of method two, let me just change the color of my pen to white. Okay, here we go. So method two, we'll be using Leibniz a way of solving uh, functions or derivatives of functions using chain rules. So again, the problem is, or the given function is f of x is equal to the square root of x squared plus 4. All right, and this could be rewritten as x squared plus 4 raised to 1/2. Okay, so I could say that u is equal to x squared plus 4. The u here expressed in terms of x, right? And f of x or f of u is equal to what's that? U raised to 1/2, something like that. Okay. And Leibniz said that you can solve for f prime of x by differentiating, okay, the function f in terms of u with respect to u. So that's fu, sorry, fu over du, right? And times the derivative of the u in terms of x. So that's du over dx, something like that. So which means that we are going to differentiate two functions here. The u in terms of x, okay, and the f in terms of u, okay? Oh, sorry, this is dfu, and the derivative of f of u over du and du over dx. All right, but however, that sometimes it's better to use y here. Okay, but it depends. Okay, so here we go. So let's get the derivative of f of u. So the derivative of f of u, df of u in terms of u is equal to, so we are talking about this. All right, and we have 1/2 u, 1/2 minus 1, and the derivative of u is something like that, and this is just equal to 1/2 u raised to negative 1/2, and this is just equal to 1, right? The derivative of u is just equal to 1. So this is equal to 1 over 2 u raised to 1/2. So this is just the derivative of f with respect to u, okay? And so we're done with this, and let's proceed to differentiating the du over dx, this one. So we have, oh, we lack space. So we're not going to deal with this, okay? I'm still dealing with the example, this example. So we have du over dx. So what's the value of u here? That's x squared plus 4, or the function with respect to x. So this becomes 2x plus 0, which is equal to 2x. So we have already differentiated the function f and u. So let's now substitute them here. So we have the derivative of f in terms of u is 1 over 2 u raised to 1/2 times the derivative of u in terms of x is equal to 2x. And let's simplify. So that's 2x over 2 squared of u. And we can, what's this? We can cancel out 2. So this becomes, sorry, x over, and let's make use of x in terms of u since the original problem is in terms of x. And we know that u is equal to x squared plus 4, x squared plus 4. So let's check if we got the same answer. X over the square root of x squared plus 4. Here we go, we got the same answer. So whichever method we use, we'll get the same answer, okay? However, if we're going to look at the solutions and the number of steps, now method one is or has a few number of steps to arrive at the final answer compared with the method two. But then again, it depends on how you're going to do it, and it depends on which method you'd like to use and you are used to doing, okay, to solve for the derivatives of the given function. But I prefer method one if you're okay with this. Okay, this is a more direct way of differentiating functions given. All right, so now I'm going to erase this because we will be solving another problem. Okay, example number 3. And kindly answer this before watching the solution, or the two methods in finding the derivatives. Oh, sorry, it's method 1 of y is equal to the cube of x squared over x plus 1. So I'm just going to copy x cubed over x plus 1, 3. Okay, so let's get the derivative of y. Now I'm going to use the more direct way of solving the derivative. So, all right, please listen carefully. So here, again, let's deal with the exponent. So this becomes 3. Okay, and copy the base, that's x cubed over x plus 1. And of course, the exponent should be subtracted by 1, okay, based on the rule. And again, since the base here is a function, another function, all right? Although even if it's not a complex function, we still need to differentiate this, just like the one we did here. Let me go back. Oh, where it is. Here, something like that, this one. Okay, even if it's not simple, we still do this, but this is just equal to 1, so that's sometimes we omit this step. However, it's just like technically you're still doing it. You already knew that it's equal to 1, that's why you skip that step. So we need to differentiate the inner function, x cubed over x plus 1, all right, and prime, which means we need to differentiate this. So let's proceed. So 3x cubed over x plus 1 raised to 2. And how do we differentiate this? This is a quotient, right? Quotient of two functions, x cubed and x plus 1. So we need to use the quotient rule in differentiating functions composed of numerator and denominator. Okay, so we have the log the high minus high the low over log or log squared. So we have x plus 1 times the derivative of x cubed, that's 3x squared. So let's do it directly. All right, minus the log the high minus high the low. So copy the higher function or the numerator and differentiate the denominator, that's 1 plus 0. All over lolo, or the square of the denominator. Here we go. So this is now our direct way of solving this. Okay, so let's proceed. Let's simplify. So x cubed over x plus 1 square. And let's simplify this. This becomes what? 3x cubed plus 3x squared minus x cubed all over x plus 1 square. Okay, and let's simplify again. So let's copy. This is y prime. 3 times x cubed over x plus 1 square times, oops, let's do this. Let's simplify. This becomes 2x cubed plus, oh, sorry, 2x cubed plus 3x squared. 2x cubed plus 3x squared all over x plus 1 square. Right, let me just check 2x cubed plus 3x squared. There we go. So we're correct. And we can still simplify this. Okay, so this becomes 3. Oh, sorry. My pen is not moving again. Oh, wait a minute, guys. Okay, here we go. So 3x raised to 6 over x plus 1 square. Okay, I'm just simplifying the first factor, the first two factors here. And this one is times, I can factor out the x squared 2x plus 3 all over x plus 1 square, right? Okay, here we go. So I think we can simplify this more. Okay, here we go. So we have 3x raised to 6. Oh, sorry, raised to 8. That's 6 plus 2 is equal to 8. 2x plus 3. And I mean, multiply the denominator, raised to 4. So this is now our answer. 3x raised to 8 times 2x plus 3. Okay. Oh, there we go. So let me just check this one. All right, so we got 3x raised to 8 times 2x plus 3 all over x plus 1 raised to 4. Okay, so this is what we got with the use of method 1. Now, we can also use method 2 here, all right? Or I'd rather be using another method instead of the longer method used by Leibniz. Okay, however, it can still be used to find the answer. But I just want to simplify this first before differentiating. Okay, so let me, oh, I don't have enough space to do that. Okay, so let me just allot space for this.